Vectorial kernels. The most popular general-purpose kernel functions are, for example, polynomials of degree q, that is k of x to the t x is equal to x transpose times x to the t plus 1, then to the degree q, where q is selected by the user. For example, when q equals to 2 and d equals to 2, k of xy is equal to x transpose times y plus 1 to the square, which is equal to x1 y1 plus x2 y2 plus 1 to the square, which is equal to 1 plus 2 times x1 y1 plus 2 times x2 y2 plus 2 times x1 x2 y1 y2 plus x1 squared times y1 squared plus x2 squared times y2 squared corresponds to the inner product of the basis function. This is developed by Cherkassky and Mueller in 1998. Phi of x is equal to the transpose of the following vector: 1 square root of 2 times x1 square root of 2 times x2 square of 2 square root of 2 times x1 x2 and then x1 squared then x2 squared. An example is given in figure 13.4. When q is equals to 1, we have the linear kernel that corresponds to the original formulation. Figure 13.4, the discriminant and the margins founded by a polynomial kernel of degree 2. Circled instances are the support vectors. Now, kernel, so an example is given in figure 13.4. When q equals to 1, we have the linear kernel that corresponds to the original formulation. Radial basis functions, k of x to the tx is equals to the exponentials of minus times the square of the norm of x to the transpose times x divided by 2 times s squared. Defines a spherical kernel as in a Poisson window, chapter 8, where x to the t is the center and s supplied by the user defines the radius. This is also similar to radial basis functions that we discussed in chapter 12. An example is shown in figure 13.5, where we see that larger spreads smooth the boundary. The best value is found by cross-validation. Note that when there are two parameters to be optimized using cross-validation, for example, here c and s squared, one should do a grid factorial search in the 2 dimensions. We will discuss methods for searching the best combination of such factors in section 19.2. One can have a Mahalanobis kernel generalizing from the Euclidean distance. That is, k of x to the tx is equals to exponential of minus 1/2 times x to the transpose times x to the t minus x, then to the transpose, then times s to the minus 1, then times x to the t minus x again. Figure 13.5 is the boundary and the margins founded by the Gaussian kernel with the different spread values s squared, and we get smoother boundaries just with larger spreads. Now back to that, where S is a covariance matrix, or in the most general case, that k of x to the tx is equals to exponential of minus times d of x to the tx divided by 2 times s squared. For some distance function d of x to the tx, so d is the distance function. Also, there are also other choices, like sigmoidal functions. K of x to the tx is equals to the reverse of the tangent function of the input parameter 2 times x to the t times x to the transpose times x to the t plus 1, where such a function has the same shape with the sigmoid except that it ranges between minus 1 and plus 1. This is similar to multilayer perceptrons that we discussed in chapter 11.